All right, so 2.6, we're getting into what are called rational functions, and we're going to focus on end behavior today. So a rational function is basically, it's the quotient. Quotient means divide. You're going to see these as fractions. So you're going to see a fraction of two polynomials. Okay. So it's a fraction with x's on the top and x's on the bottom. That's what I mean when I talk about a rational function. So here, this is like a formal definition of it. We have f of x over g of x. Those are both polynomials. But notice it says g of x is not equal to 0. Why could I not have g of x equal to 0? Why is that important? Where's g of x located in the fraction? On the bottom. Can you divide by 0? Nope. All right. So these are just some examples of rational functions that you might see. So what we're really going to focus on today is talking about the end behavior using the limit notation. So the limit as x approaches infinity, what we did previously, of a rational function. And that also correlates and has to do with horizontal asymptotes. So horizontal this way. Asymptotes are like those imaginary lines. So if you look at the graph, your graph gets really close to this imaginary line, but it never touches it. That's going to affect the end behavior. All right, so the end behavior of a rational function it's based on the leading terms of the numerator and denominator. So up here, if I look at this example, a leading term of this numerator is x squared. It's basically the whole term that's in the front, the one that has the highest exponent. The rest of that really does not matter in terms of our end behavior. So like this one will be x squared and 3x. 2x squared and x cubed. Basically, we're just going to be looking at the front. Okay. So a couple things that we will be looking at. This n, this is the numerator degree. So the degree of the numerator, I'm going to call that n. D is the denominator degree. And then you'll also see A and B, letters A and B pop up. That's talking about the leading coefficients. So the numbers in the front in the very, very front. So the number in the very, very front of the numerator we call A. The number in the very, very front of the denominator we call B. So if I say use A and B, you need to come back and reference this, or N and D. Okay. So there's 3 different cases that we're going to talk about. All of them are based on the numerator and denominator degree. One of them, those degrees are equal. One of them, the numerator is bigger, and one of them, the denominator is bigger. So 3 different scenarios that might pop up. So case 1, if the numerator degree is equal to the denominator degree. Okay, so an example of that would look something like this. 8x squared minus 1 over 2x squared plus x minus 3. you can see how the largest exponent on both the numerator and denominator, they're equal. If this happens, that means that this function has a horizontal asymptote at y equals a over b. And remember, a over b are these numbers in the front. That's a, that's b. So this function, this example, would have a horizontal asymptote at y equals 8 over 2, which is y equals 4. So I don't know, I just made up this example, so I don't know how good it's going to look in the graph, but let's see. 8x squared minus 1, 2x squared plus x minus 3. Let's see if it gives us anything. So right here at 4, there's an imaginary, an imaginary boundary basically, that these blue lines are not going to ever touch or cross over. So these blue lines will get really, really close to that number. Like, it'll be so close that if you were looking at a calculator, it would even look like it touched it, because the calculator, you know, is only so good. But an asymptote means it really doesn't actually cross over that y equals 4. If I were to look at the table and I were to scroll, I would never see a 4 on the y side. That's probably where I see an error. That probably might be where that 4 came in. So you'll never see a 4 there. So that also tells us about the end behavior. If you have a horizontal asymptote at y equals 4, then your end behavior, your limits, are going to be equals 4. So our end behavior on rational functions are not going to be either positive or negative infinity. So this one would be the limit as x approaches negative infinity of f of x. So the end behavior on the left side is equal to 4, and the limit as x approaches positive infinity of f of x equals 4. So what that means, if I go back to my equation and I start plugging in like negative 100, negative 1,000, negative 10,000, I keep going like negative more and more and more, and I plug those numbers in for x, it's going to get really, really close to 4. On polynomials, those numbers may have just kept getting bigger and bigger and bigger. But on these, it's going to get really, really close to 4. So let's see. If I do negative that, store x, and then I type in 8x squared minus 1. I'm typing it in like this instead of a fraction because I want my answer to be a decimal. Divided by 2x squared plus x minus 3. So it actually does give me 4 because it's so close to 4. Let me try a smaller number. So see how that's like really, really close to 4? Yeah. If I could do the same thing, I could do positive 10,000, store x, and it's still really, really close to 4. Okay, so the bigger my number goes, the closer it's going to get. Eventually, your calculator would just say 4 because it, it only has so much space. So that's if the numerator degree is equal to the denominator degree. Now, if the denominator degree is bigger, so d is bigger than n, the denominator is bigger, Here's an example. X minus 2 over x squared minus 9. My numerator degree is just 1. That x has an imaginary 1, whereas my denominator has a 2. The degree is 2. In all of these cases, there's a horizontal asymptote at y equals 0. So, this one has a horizontal asymptote at y equals 0. Horizontal asymptote at y equals 0. Which means my limits, my end behavior, are both going to be equal to 0. If I were to plug in 10,000 to both of those, for those x's, I would get a number really, really close to 0. Or 100,000, or a million, or a trillion. I get a number close to 0. This is really more memorization than anything. You just have to memorize these rules. Now the last case, I should say case 3, is if the numerator degree is bigger than the denominator. Okay. So for example, 5x to the 5th minus 4x plus 3 over x minus 2. An example like this, there are no horizontal asymptotes. For the end behavior, it's a little bit more complicated. So what you have to do, your end behavior is going to follow the rules that we learned in polynomials, like talking about the leading coefficient, if it's positive or negative, and if the degree is even or odd. So what we do is we look at the line y equals, and then a over b, this would be 5 over 1, so a over b would be 5, x, and then you subtract your exponents. So I would have x to the 4th. So my end behavior is going to follow the same rules as the function 5x to the 4th. Okay. So I could look at that. 5x to the 4th. Notice both sides, the arrows are pointing up, so your limits would both be equal to positive infinity. Your rules, we learned that you probably would have to have those memorized. I can't tell you for sure on the AP exam if this is going to be calculator or non-calculator. So you need to memorize the rules. There's a lot of memorization. Those are in the Quizlet. That's why it's important that you're practicing them. So as x approaches infinity of f of x equals, this is talking about the left side. So the left side is pointing up, so it's equal to positive infinity. And then the right side was also pointing up, so it's also positive infinity. So we just have, I don't know why that was blank on the back. We just have several examples that we're going to do. And you can refer back to this front page Even if you want to rip them apart, that's fine too, so that you can look. So you first, when you see a problem and it's asking about the horizontal asymptotes or the end behavior, you need to figure out, are the degrees equal? If not, is the numerator or denominator bigger? So on this one, my degree of the numerator is 2. The degree of the denominator is 2. So N equals D, which in our notes was case 1. So if you can look back at case 1, there's a horizontal asymptote at A over B. So I have a horizontal asymptote. I'm just going to put HA at Y equals, what's my A? What's my B? 5. So Y equals 3 over 5. So 3/5. So then your end behavior, both of your limits are going to be equal to 3/5. So the limit as x approaches negative infinity, so as x is getting more and more and more negative, that's on the left, of f of x is equal to 3/5. And the limit as x approaches positive infinity of f of x, that's the right side, is also equal to 3/5. Number 2, the degree of my numerator is 1, and the degree of my denominator is 2. Are they equal? Nope. Which one's bigger? The bottom. Denominator D is greater than N, which was case 2. HA at Y equals what? 0. If the denominator is bigger, you have a horizontal asymptote at Y equals 0. Which means that both of your limits are equal to 0. The left and the right. The limit as x approaches negative infinity of f of x equals 0. And the limit as x approaches positive infinity of f of x equals 0. Again, all that means is that the bigger is, if I keep putting in bigger and bigger and bigger and bigger numbers into x, into this equation, it's going to come out really close to 0. If I put in smaller, 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 it's going to get closer and closer and closer to 0. Number 3, I have a degree of 2 in the numerator and a degree of 1 in the denominator. So my numerator is bigger. Those were the ones that were a little bit trickier. There's no horizontal asymptote. But we need to write that equate that y equals. So it was a over b, right? So 2/5. Doesn't really matter what that number is, except that it's a positive number. The positive number is what affected our end behavior. X to the first. 2 minus 1 is 1. So we have a positive leading coefficient and an odd degree. A positive leading coefficient and an odd degree means on the left it's pointing down and on the right it's pointing up. Those are the rules we learned. So the limit as x approaches negative infinity. So on the left it points down, which is negative infinity. And on the right, so this is just how I say what's happening on the right. It points up, so positive infinity. Any questions? All right, let's do some more examples. All right, number 4. So your degrees. Which one's bigger? The bottom. This one, if there's no x at all, your degree is 0. So you have a 0 on the top, 2 on the bottom. So the denominator is greater. The denominator is greater, which means that there is a horizontal asymptote at y equals 0. Which means that both of your limits are equal to 0. Number 5. Which degree is bigger? They're the same. So n equals d. So there is a horizontal asymptote at y equals what? 4 over 8, which is 1/2. So the limit as x approaches negative infinity of f of x. So this is the left side in behavior is 1/2. The right side in behavior is also 1/2. Right, number 6. Which one's bigger? Denominator. If you have a negative in the front, that's the same thing as if you just put it either in the top or in the bottom. Sometimes it's easier to make it negative 4 over 2x plus 1. So if the denominator is bigger, we have a horizontal asymptote at y equals 0. So both of your limits are equal to 0. Good. I want you to try 7, 8, and 9 by yourself. Okay. Here's number 7. you should have a horizontal asymptote at 1/3, which means both of your limits, the left and the right, are equal to 1/3. Any questions on that one? Okay. Number 8, your numerator degree was larger than your denominator degree because you had a 4 on top and a 3 on the bottom, which meant there was no horizontal asymptote. So then you had to figure out, okay, you know these, your end behavior is going to be to the infinities, but you had to figure out how it works. So you had to look at the polynomial -3x. I did -3 divided by 1, and then 4 minus 3 to get x to the first. So I'm thinking back to lesson 2.5 when I learned the end behavior of a negative leading coefficient and an odd degree. If you have a calculator and you can graph that to look on the left side, does it go down or up? And on the right side, does it go down or up? But if you don't have a calculator, you gotta have the rules memorized. And so on this one, I think I did it backwards. Yeah, I did. Should be positive and then negative. Positive infinity and then negative infinity. So on the left side, your arrows would be pointing up, which is why I put positive infinity, and on the right side they'd be pointing down, which is why I put negative. And then number 9, the denominator degree was bigger, so you have a horizontal asymptote at y equals 0, and both of your limits are equal to 0. Let's see. 10 and 11. This one's looking at a picture. Look to see if there's a horizontal asymptote. This one, there's one at y equals 2. So both of your limits would be equals 2. Because the farther I go to the right, this line is not going up forever. This line is never going to pass 2. That's why the end behavior goes to 2. It gets as close to 2 as it can. And on the left side, same thing. It's getting close to 2. It's not going down forever because it's never going to cross over that barrier. So the limit as x approaches negative infinity of f of x equals 2. And the limit as x approaches positive infinity of f of x equals 2. And then this one has a horizontal asymptote. It does not copy well, but you can kind of see the lines there at -1. Alright, the last thing I'm going to throw in, and these aren't too bad, are slant asymptotes. So not horizontal, one that's like a crooked line. Right? There's no way, or we're not going to go over a specific way on finding that exact line, but we're going to get close. So a slant asymptote, you have one of these if the degree of the numerator, so the degree of the top, is exactly 1 more than the degree of the denominator. So like if you have an x to the 5th over x to the 4th, an x squared over an x, that would give you a slant asymptote. What we can do right now with what we know is we can't find that exact equation of that slant asymptote, but I can say that it's it's parallel to y equals a over bx. So I can tell you it's parallel to a line, I can get kind of close. So we want to know this last question, which of the following function has a slant asymptote that's parallel to 1/2 x? So two things need to happen. Number one, my degree of the numerator has to be exactly one more than the degree of the denominator. If that's not the case, then it's out. I don't have a slant asymptote there. And also, your a or b has to be either 1 over 2 or 2 over 4 or 3 over 6. It has to be a 1/2 fraction. Okay? So let's look at option 1. Is my degree of the numerator exactly 1 more than the degree of the denominator? No. This one has no slant asymptote. Doesn't have one at all. What about option 2? Does it have a slant asymptote? No, it does not. So same thing there. What about option 3? Is the degree of my numerator exactly 1 more than the denominator? Yep. Is my a over b simplified to 1/2? Yep. Option 4, is my numerator degree 1 more than the denominator? Exactly 1 more? Nope, it's a 4 over 2. 4 is not 1 more than 2. So that one doesn't have a slant asymptote. So the only one that it could be is option 3.